They're not all the same length, and I think that's why it looks really tight and weird.
We're in section 4.4. Do you have any questions on the homework that's due this weekend before we continue on? Yes. Okay.
My gallery has like 13 vertices or whatever they're called, and I can't figure out the number of.
Did you say number 3?
No, 4.2.
4.2. And which one?
The third one.
Third one.
Yeah, I have 15 for mine, and I can't figure it out.
Oh, I see. So you take 16 and divide it by 3. Oh, you have the number 15?
Yeah.
So you take whatever your number is and divide by 3. So, for example, 15 divided by 3 is 5, and that would be the most that you would need. So that's what the art gallery theorem says. This one was 16 divided by 3 would be 5.3. So you would still pick 5. You put the whole number there. Okay, the 5. Any other questions? Okay. Well, we were looking at 4.4, looking at different kinds of symmetry. One of the things that we aim for in this class is to look at how mathematicians are thinking when they come up with these ideas and see if those ways of thought can help us in our own fields. So the life lesson for this section was specifying the meaning of a familiar term or notion can open our eyes to new possibilities and ideas. So we specified what it meant to have symmetry in the plane, and then we actually ended up with 2 symmetries in the plane, and by giving those precise definitions, then you can work with them. And so that's something you might keep in mind as you go in your own field. So let's talk about those types of symmetry. We had rigid symmetry and symmetry of scale. So who remembers what rigid symmetry was? Yes?
Is a motion on the plane that preserves the pattern and does not shrink, stretch, or otherwise distort the plane.
Exactly. So a motion of the plane that preserves the pattern without shrinking, stretching, or otherwise distorting the plane. So you could see those rigid symmetries using the transparencies. So the transparency could move down for this particular example with hexagons, or it could move to the right, or it could rotate. Or it could even flip. So those were all examples of rigid symmetries where you could take a transparency and move it around and you're going to see the same shape, the same pattern. You're not going to distort it. Okay, perfect. So we had, with symmetry of scale, rather rigid symmetry, we had the hexagons, we had the squares, and we had the triangles. Then the other symmetry we had was symmetry of scale. Who remembers what was that one? Yes?
That was by grouping shapes together and or tiles, making a super tile. You could increase the size but still have the same shape that then would fit in the pattern.
Exactly. So you could put the tiles together to make super tiles that were the same shape. So here we put 4 triangles together. So we made a super tile with 4 tiles. And if you were to pattern those 4 tiles as their own triangle, you would get the same pattern just at a bigger scale, and you could shrink it down and it would be exactly the same scale. Yes?
And would that still be rigid symmetry? It would have to still have the...
Yes, so exactly. So this particular pattern with the tiling of the triangles had the symmetry of scale, where you could make a super tile, but it also had the rigid symmetry, because if you took a transparency of it and laid it over top, you could move it up, down, flip it. You don't have to have all of these types of rigid symmetry. If you have one type of rigid symmetry, you have rigid symmetry. So we looked at some online, more interesting tilings by M.C. Escher, and those were more interesting, and you could see just usually one type of rigid symmetry, though, maybe 2. So we have two kinds of symmetry of scale. And now the question today is, let me write it down so I don't write it backwards. The question is there tiling with symmetry of scale? Is there a tiling with symmetry of scale, but no rigid symmetry? Is there a tiling with symmetry of scale, but no rigid symmetry? So we looked at just one tiling that did not have a symmetry of scale, and that was the hexagons. We saw that we could put hexagons together, but they weren't going to make another hexagon. So we couldn't get a super tile, a larger hexagon shape out of putting smaller hexagon shapes together. But now we want the other question. Is there a tiling that has symmetry of scale, but no rigid symmetry? So the other tilings we looked at that had rigid symmetry, that had symmetry of scale, had rigid symmetry, and that was the squares and the triangles. They had both rigid symmetry and symmetry of scale. Okay, so I'm going to put this last picture down and ask you what types of symmetry you see in that. So I brought some extra ones of these because maybe some of you didn't bring yours with. So I'll send some down here. Does anybody in this row need one? Anybody down here? Anybody else? So tell me what kinds of symmetry you see there. Or think about it. Well, maybe we should go one at a time. So the first thing we looked at was symmetry, rigid symmetry, but I didn't give you a transparency, so that's kind of hard. How would you describe this pattern just if you saw it on a floor somewhere?
Busy.
Busy, yeah, I think it is busy, yeah. Busy or chaotic. So with the Escher online pictures that we looked at, it was easy to look at rigid symmetry. You could easily slide up like a fish and a dove on, or a fish and a bird on top of another fish and a bird, or slide a horse down to another horse. Can we do that here? I can't even line it up the way it is. I think I have my transparency upside down. There, that's the way it goes. Okay. It turns out that you cannot. You can't slide this around. This does not have rigid symmetry at all. I can't turn it and make it match. I can't flip it and make it match. There's no rigid symmetry here at all. And we'll see why that is a little later on in class. Okay, well then let's look at the other symmetry. Is there symmetry of scale? Can you see larger? Yeah, you can. I see heads nodding. Well, we're going to examine that more carefully. So this is called the pinwheel pattern by Penrose. He discovered this in 1994, and it is tiling that has symmetry of scale, but no rigid symmetry. So it's a Penrose pinwheel pattern. Whoops, and I'm off screen, sorry. The Penrose pattern. So let's look at this more carefully. First we're going to make a right triangle that has symmetry of scale and a rigid symmetry. So if we take and make a right triangle, we can make a new super tile of that right triangle. One way to do that would be to make another triangle right here. I don't think that's the way I wanted to do it. Oh, I guess it works okay, because then I can go like this, right? So I have 1, 2, 3, 4. Okay, so this is a right triangle that I can make another copy of. So my original one was number 1. I put 4 together, and I made a larger copy of number 1. And because I was able to do that, I can repeat that process. So if I took another color, I could make my number 2 the same way I made number 2. Whoops. So like 1, 2, and then my tip here, 3, and then 4. Okay. So I could continue tiling the plane like that, and if I filled in the whole, these are super tiles, but if I filled in the original little tiles here, I would see that I have a rigid symmetry. So I'm not going to do that whole thing, but you can. Okay, so this 4 tile pattern will pattern the whole plane in such a way that it has rigid symmetry and symmetry of scale. So if you continue making that yourself, you'll see it doesn't have that busy appearance that the pinwheel pattern does. So we're going to look at the pinwheel pattern next and see why that turns out to have the why it turns out to have the symmetry of scale but not rigid symmetry. So the pinwheel pattern has a particular proportion in its triangles. They're called the golden triangle. And we're going to draw it to scale. So you'll need 1 piece of paper loose to use as your measuring stick, okay? And we'll use the other paper that we're drawing with. So I'm going to make a triangle that's 1 unit tall and then 2 units wide. So that's why I can use my paper to measure, because I could do this in inches. I can make it 1 inch tall and 2 inches wide, or centimeters, 1 centimeter tall and 2 centimeters wide. But we're all using paper here, so you can use it 1 line tall and 2 lines wide. Let's see what the hypotenuse is then. So the 2 legs are 1 and 2. Let's see what the hypotenuse would be then. So 1 squared plus 2 squared equals c squared. 1 plus 4 is c squared. So 5 is c squared. And that makes the square root of 5 equal to c. So this triangle has the lengths 1, 2, square root of 5. So we'll use those particular lengths, and then we'll create a super tile, but we're not going to use 4 tiles, we're going to use 5. And the ability to use 5 and still get a right triangle with the same proportions depends on the shape that we use, the 1, 2, square root of 5. So let's go ahead and build a super tile. So go ahead and start with a single tile again. That's the proportions 1 high, 2 wide. So I'm just using my lined paper to measure 2 wide. And then I can add my second one by just going straight up to the line here and making a rectangle. And then my third one is going to be a reflection of number 1. So I'm going to take my third one and reflect it across the line. So I'm making that one tall as well, and it's too wide because I made number 1 too wide. So number 3 is also too wide. So far these are all 1, 2, square roots of 3. You can see they're all 1 line tall, and if you use your paper to double check, they're 2 lines wide. And now I'm going to make the tip. So I need to measure again, because now I'm going to make the tip over here, and it has to be 2 lines wide. So measure 2 lines wide over there. So that's the right triangle, but it's not the Penrose pattern, okay? So we need one more triangle to make the Penrose pattern. The way we add it on is to make a triangle 1 wide off to the side here, right here, so 1 wide. Because this is number 1 and number 3 together make 2 tall, right? So those are 2 tall with the 1 and 3 together. And now I'm going to make 1 wide. So I'll have a triangle 1 wide and 2 tall. And then when I connect, this will be square root of 5 as well. This makes a right triangle because triangles 3 and 5 have their acute or their smaller angles put together. And when you have a right triangle, the 2 smaller angles add up to 90 degrees. In the right triangle, you have the square corner that's 90 degrees, and then you have these 2 smaller corners that add up to 90 degrees. So let's measure this now. Okay. Triangle 4 was 2 wide, 2 units wide. So there's 1, 2, and then triangle 2 is 2 units wide, so 1, 2, 3, 4, and then triangle 5 had 1 unit this way. So we have 5 across here. And now on triangle 5 over here, this hypotenuse on triangle 5, well, that's square root of 5. We know that because these are all 1, 2 square root of 5s, and that's the hypotenuse length, square root of 5. And then on triangle 4, there's a hypotenuse right here, square root of 5. And on triangle 5, there's a hypotenuse there, square root of 5. So altogether, this is 2 hypotenuses, or 2 square roots of 5. So let's just look and see that the proportions of this triangle are still the same as the original proportions. So we have the hypotenuse is the 5 this time. The right angles formed down here by number 3 and number 5 connecting. So we have square root of 5 for the short side, 2 square roots of 5 for the longer leg, and then 5 for the hypotenuse. This is just a multiple of your original lengths. So you can always build a triangle with the same proportions just as a multiple of the original. So we take the original, 1, 2, square root of 5, and multiply times square root of 5. So our new triangle is square root of 5 larger than the original one. So square root of 5 times 1 is square root of 5. Square root of 5 times 2 is 2 square roots of 5. And square root of 5 times square root of 5, that's 5. So the new triangle that we made that's larger is square root of 5 times as big as the original triangle. So we're keeping the same scale. We're keeping a symmetry of scale, and we found a way to make a super tile. So since we have a way to make a super tile, we can use this super tile in the same fashion that we used the original tile to continue tiling the plane. So we can take this super tile and make it be where number 1 is, and then we could build a number 2 off of it, and so on, and keep going. Well, rather than doing that, I think we're going to look for those super tiles in the handout that you have. Okay. So first we'll try and find a 5-tile super tile, and then we'll try and find a 25-tile super tile. And if you're really focused, you can find bigger ones than that. But because there's no symmetry of there's no rigid symmetry, it's harder to find the bigger ones. So let's just start. Let's go ahead and try. Okay, so pick one out. Pick out what you're looking for. What helps is if you look for this T shape, and then that T shape between tiles 1, 3, and 5. That T shape can help you find your super tile. So I see a T right here. So I'm going to think of that as tiles 1 and 3, and then where would 2 be? This has to be 2 because my tip is right here. So finding the T's can help you find where the 2 is, and then you can find the tip and the tail. Okay. Now I'll come around and help you find one. After you find one, see if you can find one the next size up. So this is 5 tiles. Now I want to find 25 tiles. So I'll pick a different color. And I see a T here. So I'm going to work with these 3, I hope. It's actually, it's not as easy to do as you would think. But I think I am okay here. I think I found it. Okay. So as you put 5 tiles together, make sure there are 5 in each super tile to make a super tile with 25. So I'm going to come around and see how you're doing. And we'll talk about why it's not as easy as it looks like it should be after we try a bit. So raise your hand if you're stuck, otherwise I'll just kind of randomly walk around. Yeah. So I wonder if you need this part. I think you need this part. So 1, 2, 3, 4, and you need this part.
Oh, yeah.
Oh, and so you were doing the same one, and you did catch that. Okay, can you find the smaller ones in there too? Okay. Yes. Oh yeah, so here's a T. There. Yep. Yep. So then you need the layer above it. Yeah. So that's 1, 2, 3, and then here's a tip. And here's a tip. Do you need that handout? Oh, okay. So this is something I would ask you to do on a quiz. So there's always, this will be the same picture on the quiz because this is the picture I have. So feel free to download it on D2L and make copies and practice. Does anybody else need a copy? So you did by 5 though. And then this looks like a T to me right here. So that would be 2. And this is 1. And this is 1. So it's like, where do you go from there, right? Let's see. So 1, 2, 3. No. Yeah, this is 1 and 2. It's not bad though, because then you got 1, 2, 3. So I think you're actually, so 1, 2, 3, 4. Oh, yeah, you have one. Right there. Yeah. It's 2 of them. And there. And then this one goes in there also. Oh. Yeah. That one. And then that one. Feel free to help each other out, okay? Because I'm not getting around to everything. Okay, so there's, that's 5. 1, 2, 3, 4, 5. 2, 3, and then there's a 2 here. And then the tail. And that's 5 in the tail.
This one here has the 25.
That's what's working out. So you found a key.
No, it's right with this one.
So that was 2 super tiles.
This those.
That's 2. And then yeah, and then what?
Yeah.
Okay, good. Okay, good. I don't think so. Because there's like 3 in a clump, and then you have a tip and a tail. So I'm not sure that we can go on from this. I think you might have to give up on that area and try a different area. If one of the areas you're working on doesn't work, then give up. Try another area. Raise your hand if you're stuck, okay?
I'm finding bigger.
Oh yeah, you can find another one. Can you find the smaller ones though inside of it?
Yeah, I did that. I was working on them.
Okay, so you can find the 5. Can you find 25? So
Yeah, right there.
on the quiz, I'll be looking for 25.
This one right there. I counted 20.
1, 2, 3, 4. Yep.
And then I figured, I was like, wait, I said bigger battery. But
Okay, so I'll look at yours after class if you want, or you could email me, online students, if you're having trouble, and we'll see if we can work it out, okay? So let's see, why isn't it as straightforward as you might think? It's because we're lacking rigid symmetry. So we're not going to look at a proof that it's lacking rigid symmetry. The proof is quite hard, but we'll just demonstrate why it doesn't work by looking at the 5-tile superlit tile. So as you tile the plane, all of these tiles have to be constructed in this fashion. You can't try and just put super tiles together in some other way, or it will not have symmetry of scale throughout. The reason is if you put in this interior place one of the other triangles, like say you put number 1 there, the other triangles in the super tile cut up what you have going on. So it has to be made exactly in this way. None of the other tiles can be placed in position where the interior one is. The interior one has to be that interior one, or else as you try and place the other tiles, they cross what you're working with already. So you can see if you put number 3 there, you get a cross here. If you put number 4 here, you get this number 3 crossed. So there is only one way to tile the plane with the pinwheel tile, and it has symmetry of scale, but it does not have rigid symmetry. So I hope as we're looking at symmetry in different shapes, that as you look around the campus and the other buildings and places where you're walking, you're seeing triangles and squares leaping out at you. Well, not physically, that would hurt, but that you're noticing them. Let's go on and take a look at section 4.5. Does anyone have questions before we do that? In 4.5, we're looking at the platonic solids, and it's nice to see so many platonic solids here. You'll need those today and Monday as well. The question in section 4.5 is a question that we looked at in 4.4. What's the most symmetric figure you can draw in a plane? And then, more specifically, what if you can only use straight lines? So in 4.4 we talked about a square being symmetric, because you can look at one half and it looks the same as the other half, and in many different areas. And we also talked in 4.4 about a circle being symmetric, again because half of it looks like the other half. So section 4.4 moved quickly away from the symmetry of a single shape into the symmetry of an entire plane. Well, now we're looking more at just a single shape again in 4.5. What kinds of shapes would be symmetric besides a circle or a square? Plus, before we do that, I almost forgot, can you take a photo of that super tile that you traced out? That's your drop box. Okay, so the super tile that you traced out with 25 tiles, that's your drop box. So what other shapes would be symmetric besides a square and a circle? What other shapes have one half the same as the other half? Pardon? Triangle. Perfect. Triangle. So lots of ways you can cut the triangle in half and see one half the same as the other. In particular, an equilateral triangle or an isosceles triangle. What other shapes would be symmetric? Oh, now I heard two at once. What did you say? Octagon. Octagon. Okay, so an octagon. And what was the other one?
Rectangle.
A rectangle. You have a rectangle. So we have four-sided figures. And if we're just sticking with straight lines, then we'll discard the circle. We have three-sided figures. We have eight-sided figures. Is there such a thing as a 10-sided figure that's symmetrical? Yes. Can you describe it?
Well, basically this,
It's basically that.
not,
Oh, okay.
except not like.
The flat.
Yeah, it's flat, it's not.
So it's a polygon, right?
Yeah.
Yeah. Okay. Okay. Yeah, I see what you're saying. So it's actually like kind of like the octagon, but it has two more sides slid in. So if you were carefully to draw 10 sides, all the same. So you'd have a 10-sided polygon. So we're describing a lot of these figures that are in fact regular polygons. And we're talking about regular polygons because as you held up your platonic solid, your platonic solids are made out of regular polygons. So regular polygons, all the sides are the same length. All the sides are the same length, and all the angles are the same size. All the sides are the same length, and all the angles are the same size. Well, I have a question for you about regular polygons. So we saw an octagon, that was a regular polygon, same size lengths. This triangle that I drew has all the same size lengths, so that's a polygon. The square is a polygon. The 10-sided figure I didn't attempt to draw correctly, but that should be a 10-sided polygon. How many regular polygons are there?
Aren't there infinitely many?
Good, yes, infinitely many. Now, as you add more sides, you get closer and closer to looking like a circle. But that's okay. You're still a regular polygon if you're specifying that you have straight lines, not a circle. Well, the reason I'm wondering how many regular polygons there are is because now we're looking at the platonic solids. So in 3 dimensions, what are some symmetrical shapes? In 3 dimensions, what are some symmetrical shapes instead of just 2 dimensions? Yes?
Like a cube or like a rectangle.
Sure. So a cube would be, at least before I brought it to class, when I put it in my bag it kind of lost its symmetry, but a cube would be an example of a symmetrical shape. So we're kind of thinking straight sides now because that's what we've been talking about, but certainly a sphere is symmetrical as well, right? And if we are sticking with straight shapes, then I asked you to construct platonic solids, which are symmetrical. So let's talk about the platonic solids. What are platonic solids? So platonic solids have the same regular polygons for each side, platonic solids have the same regular polygons for each side. So hopefully you, as you were making yours, you cut all the same length straws so that your sides had the same length. If any of you got a kit with only 25 straws, bring it back to the bookstore because those are from last semester and I had asked them to double that. So somebody accidentally still got
cut them into fourths.
And so you managed it? You know, they're kind of sturdier when they're small like that, so that worked out good. Okay, good. Okay. They have the same regular polygons on each side, and also the same number of sides meet at each vertex. So they're very beautiful. They have the same regular polygons for each face or side, and the same number of sides meet at each vertex. So the cube, for example, has three sides meeting at each corner or vertex. Now these platonic solids are named after Plato, so that's 400 BC about. We're studying something mathematicians have looked at for centuries, for millennia. During that time, how many platonic solids did they find? How many platonic solids are there that we know of? How many platonic solids are there? So we're looking back at the regular polygons. There were infinitely many regular polygons in 2 dimensions. Now we're looking at symmetry in 3 dimensions. Will there be infinitely many? There's at least 5, right? Because you made 5. Is there some other number in between? 5, an infinite number, 10? To think about that, I want you to think about the shapes that you're making, okay? So some of your shapes, some of your platonic solids were made out of triangles. So here's the octagon. So you see it has the three-sided figures, the triangles, and each face is a triangle, same exact regular polygon triangle, and then there's how many meeting at each vertex? Who has their octagon? How many meet at each vertex? Count your triangles. How many meet at a corner?
4.
Yeah, 4. Okay. So we're going to think about the shapes and think about how they could be constructed. So go back to the cube, for example. Three faces meet, three squares meet at each corner. Three squares meet at each corner, okay? Now you've made these, so hopefully you're kind of familiar with how it feels to put these together. Think about, could you put one together with 2 squares meeting at each corner? Or with 4? Could you construct a regular polygon, a platonic solid? Could you construct a platonic solid with 2 or 4 squares meeting at a vertex? Does it have to be 3? Could it be 2 or 4? Or maybe some other number like 5? I'd like you to think about that over the weekend. And I'd like you to bring these back some more, and we'll look at them more carefully on Monday. But before you go, I did want to get feedback on how this semester is going for you. I know you get to tell me at the end of the semester how the class went, but that's a little too late to do any good. So if you wouldn't mind, please take out a blank piece of paper with no name. Okay, this is anonymous. And write on there what you like and what you don't like in class, please. Online students, I'll be mailing you the exact same servant. Okay, so when you're done, just put that upside down right here, no name, just what you like and don't like in class. And bring these Platonic dogs back on Monday. I'll see you then.